Log on, tune in, find out. Another good idea from Cambridge.
Session with two talks on a model related to neuroscience. And the first one is by A Carrillo, and it's about nonlinear integrated amplifier neuron model analysis and numerics.
Okay, so I cannot start by thanking the organizer for inviting me to give the talk, but I will anyhow, the organizers of the seminar. Okay, so the objective of today, we have put these talks together in order to explain a bit what we are doing in this subject. We have just started, well, a year and a half ago, more or less, and so I will, in this first part, I'm going to present summary of result of two works, one in collaboration with Benoit Bertin and Maria Jose Cáceres, and the other one with Maria Jose Cáceres and Luis Tao in Peking University, that formerly was in New York University at Quran, working in this computational neuroscience group. And later, Maria del Mar will talk about more recent research, which is not finished, as is in preparation, and we are continue working on that. Okay. So what is it about? I will explain, since I guess most of you haven't seen these kind of equations. In fact, I saw them just a year and a half ago. We'll present you what are these integrate and file neural models. In fact, they are, well, as you see, from the PD point of view, they are quite, people have just looked at it quite recently. And I will mainly concentrate on certain analytic results. So I have a theorem to offer in this part of the talk, at least, and then some numerics also to explain what we expect and what we would like to understand in those models. Okay, so the outline is the following. First, a bit about the modeling. Second, I will talk about a blow-up result and some a priori estimates. The stationary states, we have some good information, but not completely understood. You will see later. I will discuss things about the linear case, and finally I will explain some numerics. I'm going to present you two different models, for you to see that there is also a graduation of models here in this field, and they have a kind of kinetic and macroscopic feeling, both of them, as you'll see in 1 second. Okay. Well, LEAF stands for Leak, Integrate, and Fire models. And you'll see in a second why this name. Okay, so what we would like to do is to model the collective behavior of a huge ensembles of neuron cells. Okay, so this is just a good picture that you take from Wikipedia of a neuron, but I'm not gonna model this in a very detailed way, because precisely we want to treat a huge set of them. So it's, if you want to do something sensible, the first thing that you should do is to try to model with very simple, each cell with very simple model. So these models basically are based on regarding the evolution of the membrane potential. That's one of the quantities that is very important for the behavior of the neuron, which is the potential across the membrane, that it may vary depending on the axon or the nucleus and so on, but in the easiest models you just consider one quantity, which you suppose uniform for the whole cell, which is the potential across the membrane. And of course that potential changes through the different concentrations of ions that you have inside the cell. The ion channels is what they allow the permeability of this and the change of these concentrations. Well, the first model for just one single neuron, in fact, it was proposed a long time ago in a thesis of a French biologist, Lapic, in which he proposed to model the evolution of the potential, of the action potential across the membrane by a simple electric circuit. Okay? So that's in fact is the starting point. So the basic leak, integrate, and fire model, why it's called like this? Well, this is my own interpretation of the papers I've read from neuroscientists and biologists on this field. So it's called leak because you assume a very simple model in which it's just like an equation for a circuit. You have a certain the evolution of the potential across the membrane follows just C times dV over dt equals the intensity. You have a kind of relaxation towards a fixed potential of the membrane if the cell will be alone. So that would be like the typical potential at which the cell would like to be. That's called the leak potential. And then you have all the relation with the other neurons in the ensemble is modeled through this I of t. This I of t will be, say, the external current, or what they call also the synaptic current, which is the current that this neuron receives from the action of the others. Well, typical values of this thing. So you have this leak potential, which is about minus 70 millivolts in typical values that have been measured. Okay, so what's the more or less the typical behavior of one single neuron? So you have that due to the action of the other neurons, it will decrease or increase, but here I just depicted a typical one. It will increase if it gets excited by other neurons, so it will increase up to a certain maximal value of the membrane potential, which is called the threshold value. And when the neuron arrives to the threshold value, it immediately discharges. Well, this is also an assumption of the model. What is true is that it discharges. It typically takes a bit of time to discharge, but it discharges to a certain value of the potential, which is called the reset value. Okay? And then it starts to doing it again and again. That's the typical behavior of one single neuron. They have a very good measurement now, and they can do really these measurements even with single neurons. I asked, and the real experimentalists, they told me, yes, we can do it. I was a bit surprised. Okay, anyhow, as I said, the I of t is the external input current. The firing voltage or the threshold voltage, I will use firing voltage or threshold voltage for the same thing. The idea is that when the voltage arrives to that value, then it fires. So that's why the name of integrate and fire, because it integrates the equation up to a time and then it fires. Okay? And the typical value is minus 50 millivolts. And then the reset value somehow is in between the firing voltage and the leak voltage. It's around minus 60 millivolts. Okay? Just to give you an idea of the quantities here in the scale. Okay, now the model for the network. I just mentioned to you what is the easiest model, in fact, that you can do for a neuron, which is the evolution of the membrane potential. At this point, I should say that there are many other models for a single neuron, taking into account ionic concentrations and blah, blah, blah. So many others, but that's simply the easiest. So let's start with the easiest. And now I have to explain you about the connection to other neurons in the network. So how to model the synapses with other neurons in the network. So this is some part of the question, how to model it. I'm going to just tell you how some computational neuroscientists are right now modeling. I'm not going to discuss, because I don't know too much, that why they really use this kind of model, but I will try to describe it and then concentrate on more the PD aspect out of it. Okay, so how they do the modeling? So they assume basically that, well, there are first two families of neurons in the pool. You are looking at a pool of neurons, and you classify them in excitatory neurons and inhibitory neurons. Are the ones that try to increase in average the potential of the other neurons are excitatory. The other ones, they try to inhibit the behavior of the potential. They're called inhibitory neurons. Then for each of them, they assume an stochastic model for the distributions of the time in which they spike. As I told you, the typical behavior of one neuron is that it increases its value, and at some point when it touches this threshold or firing value of the voltage, then it fires. So what they assume is that the times in which a single neuron, either excitatory or inhibitory, spikes follow certain distribution. They assume that it follows a Poisson process. Okay, that's the typical assumption on these times. We assume that they follow a Poisson process, and let me just explain a bit the notation. This Tij means the time of the jth spike coming from the ith presynaptic neuron. So it's a neuron that is connected to this one by synapses, and it sends at time Tij this spike. Okay? The same will be for the inhibitory neurons, and these J's are the typical strength of the synapse, and the typical, C are the number of neurons that you are considered of each type. Okay, and as I said, the stochastic assumption, the main assumption comes from the fact that they assume that the spike times, they follow a Poisson process with constant probability of emitting a spike per unit time, which is called nu. And this nu is somehow the mean firing rate of the ensemble of neurons. As I said, this is just an assumption, and there are just hundreds of papers devoted to try to verify if the assumption is correct, measuring and comparing to this, and there are other theories and so on. But nevertheless, let's take this for granted and let's work with that assumption. Good. So then you can compute for the mean and the variance of this external current that goes into the equation for the evolution of the action potential. And just by using the formulas of the mean and the variance of the corresponding Poisson process, you arrive to those formulas over there. The mean of this I of t is b times nu, where b is that quantity obtained in terms of the strength and the number of neurons of each type. So depending on the kind of neuron that you are assuming, or the right combination of neurons that you have in the pool, this b can be positive or negative. Positive is in average is excitatory, negative is in average is inhibitory. Okay? And then the variance of that process, it has this form again in terms of those quantities. And then what many people have done in order to reduce it to something which needs an analytic treatment, and all these people I mentioned here, they are not mathematicians, they are all of them computational neuroscientists or neuroscientists. Nicolas Brunel is in Paris 6, Hakim is in École Normale Supérieure, Renard, I don't know what it is, but somewhere in the US. These people are in Italy. So all these people, what they proposed is approximate the current by what they call the diffusion approximation. Approximate this process by just a Brownian motion with the same mean and variance as the I of t. Again, here you are doing another approximation that I don't think nobody has tried to look at how bad or how good is this diffusion approximation in theoretical terms. But this is what they do. They approximate this by an stochastic a Brownian motion with a drift given by mu c and variance sigma c. Okay? Well, out of that, what else? Firing rate. Yes. What about the firing rate? I had to tell you how to compute this firing rate. This nu is the typical probability in which you are going to have a jump of the voltage, so that the voltage is going to be reset to the value of the reset voltage. How do you compute that? In fact, this should be also a quantity that you are able to compute from the network, because it somehow has to be given by the network of neurons, this average number of this mean firing rate. So in principle, there is a part which is external, that you can assume that you are looking just at a very small piece of your brain and cortex, very, very tiny part. And you assume that the effect of what is outside is given you in this signal. And what is the n of t is just the internal one. How you compute it? So the idea is simple, since these neurons are building their potential up to the threshold of firing voltage. So this n of t is going to be just the flux of neurons that you get at the threshold voltage. So they are the neurons that go to the voltage, they're going to address it. So they're going to give you the mean, they have to give you the mean firing rate. So by definition, this is what these people are taking. This n of t is the flux of probability crossing the threshold voltage per unit time. Good. Yes, yeah, maybe. I will put it here. It's true. Perfect. iPhone. Good. As I said, the network is called average excitatory or inhibitory depending on the V. Okay, so now we can go to the PDE after this. Now we can write what is the PDE for that. We just use Ito's rule and we obtain the corresponding Fokker-Planck equation associated to that process. Now what we obtain will be an evolution equation for the probability of finding neurons at time t with a certain voltage V. Okay? This V takes values in principle in minus infinity. Well, that's in mathematical terms. Of course, it will be minus infinity, but okay, let's say minus infinity up to the threshold voltage. The equation, you just apply Ito's rule, is going to give you directly the red part. So the evolution of the probability density will have a drift, which with the notation I got is, well, the drift is minus the voltage plus, sorry about the capital V here, should be a small v, but apart from that it's okay. Minus V plus VL plus the average, the mu C. Remember that the mu C depends on the, well, it has that formula that I told you before. I will come back to that in a second. And then the diffusion will be the sigma C squared, the variance. And now how you incorporate the threshold voltage and the effect of going, all the neurons that arrive to the threshold voltage, they have to appear at the reset value. So what you have now is a source, which is exactly located as a delta at the VR voltage, the reset voltage, given by the how many neurons arrived to threshold value. So you have this n of t there. Now how are the boundary conditions here? No neuron should arrive to threshold value because immediately it's resetted. So you have Dirichlet there. At minus infinity I put Dirichlet, but we could just cut it and put no flux or something like that. That's just for convenience. Oh my, François, sorry about that. Good. So there is no, say, at minus infinity we fix that it decays, some initial value. And now how you compute this n of t? So in fact the idea is simple. The n of t should be the flux at the threshold. In fact, if I want to have an evolution of a probability density, I should have conservation of the integral of p with respect to v. It should be 0. I mean, the integral of p with respect to v should be 1 at all times. So this is, you want, fix you the value of n, and exactly n is what it has to be. It's the flux at the threshold value, or the firing voltage. Okay, you compute the flux there, it will be given by this, plus the corresponding term here, but the corresponding term here is 0 because of the boundary condition of Dirichlet. Okay, so you have only the n of t is given by that formula. Okay? Just to simplify my life and not to from changing from the real model that you find in the literature to a model which is somehow simpler to treat, I just get rid of constants here and I translate the voltage variable in such a way that I make appear the drift in that form. The important thing here is that the drift will be minus v plus a constant times n. Okay, so here you have a nonlinear model due precisely to this, because your drift was depending on nu, what was the firing rate, and nu depends on n, and n depends on p through through the flux at the threshold. So now the nonlinearity comes here in the drift is minus v plus this constant that is positive or negative times n. And the diffusion coefficient may also depend on n linearly. But most of the time, in fact, the diffusion coefficient in most of the works is just constant, so there is no this n dependent. So the most typical problems that you find is without this A1. But we just include it because we can do something with that too. Okay? Good. So you see, it's the first time I saw that, I said, okay, it's quite non-standard thing, because we have it's a standard Fokker-Plan equation, but we have this source with the delta, and you see the coupling, the nonlinearity comes from a boundary condition, which is it's like a nonlinear Fokker-Plan equation. You can compare it to Blasso-Poisson Fokker-Plan, but it is not, because there the nonlinearity is an integral over the function. It's not a boundary condition. Here is a boundary value. It's more complicated than that. But you have less regularity with that. Okay? Anyhow, the comparisons with other models will come later in the other talk, so I will not go into that detail. Good. So that's the problem. That's the PDE model. Now what we can say about it. Okay, so, sorry. I have something more to offer in the modeling part. I'm going to show you another model that we have been working also. In that model, I don't have yet any analytic results, but we have done some numerics. And I think it's the right moment to show you now this. This model, if you want, is an improvement of the previous one. In the previous one, we assumed just that the model of the neuron is given by the membrane potential, V. So now you assume something more complicated, which is a system of two, where also what it varies now in time is the coefficient that was multiplying the relaxation towards the based potential. This in computational neuroscientist literature is called the conductance. It's capital G. And there are also conductance models for neurons. And one of them is the one that I show you here. So you have basically the same effect on the membrane potential. So you have some part which is relaxation towards some value. Let's call it the reset in this case. In fact, here the reset and the leakage is taken to be the same, to simplify. And then there is another relaxation towards another value for another reason. Okay, it's not important now. And then you have also an evolution of the conductance in time. In fact, the stochastic part, it doesn't appear in the first equation, but it appears in the second. So the connection to the synaptic current appears just in the evolution of the conductance. Okay, you look at it and you think that, again, I do some kind of diffusion approximation of this I of t. This I of t will be the same as before, okay? Nothing changes there. So you look at it and you see that this, if to any model that we have in kinetic theory is similar, it's similar to the kinetic Fokker-Plan model, because you have like the Ronan motion in the other variable, okay? So, this model was proposed or used in diffusion approximation by Kai, Tao, Rangan, and McLaughlin, all of them from the Curran Institute. And some years ago, you have in that paper these equations written. And again, what they propose is to have a PDE for the evolution of the probability density now in voltage and conductance, where the V now is in this interval. They restrict to the interval V reset, V firing, and G is a number between 0 and infinity. And the model is, again, well, a kind of kinetic-like equation. Well, I write it like a kind of conservation of the total number of neurons. The flux in the voltage variable is given by that form. The flux in the conductance variable is where the nonlinearity appears, because it's when you have this mean value and this variance. And again, this drift and variance of the process is again, before that, boundary conditions. Here, the boundary conditions are done, I explained in words because it's easier to read. In the G is that no flux at 0 and infinity, okay? The neurons, they don't go out of that. They have always a positive conductance. And in the voltage, everything that arrives to threshold appears in reset. So it's a kind of periodic thing, in a sense. That's how they impose boundary conditions. And again, those two functions of t, they are affine functions of the mean firing rate. And the mean firing rate is, again, the total flux of neurons at threshold voltage. This Vt should be the Vt is the Vf as before. V threshold, V firing is the same. So you just take the flux of all neurons at the threshold voltage, and you integrate in the G because now you have another variable, and that is what is involved in these two quantities. So the nonlinearity comes through this average value of a boundary condition. Okay? So it's a kind of second order model in this story. Okay, so now.
One question in the model.
Yeah.
You don't have boundary conditions for the F or the V or the G.
No, you have for the G2. I said no neurons going through the boundaries in the G. G0 and G at infinity, there's no. So decay at infinity, zero flux. At 0 in G and in V, everything that goes up comes down.
No boundary condition.
That's it. I mean, it's when you have to interpret those boundary conditions. In fact, I mean, one has to read what it means. This, and then it implies, for instance, that P has to be 0 in certain set. But it comes from that. So it's more. I agree. It's more difficult to see even if it's well posed. No problem. Okay. Okay. So let's concentrate in the first one because I don't have that much time. So I'm going to offer you some analytical results that we know. First, blow up and a priori estimates. Okay, I already said blow up. I have to understand what it means this. So first, I'm going to tell you in which sense, of course, the first thing I have to say, in which sense I'm going to consider a solution of this problem. So the problem here is that the nonlinearity, as I said, comes from a boundary condition. So, so in this way, that's why I say that we have a solution. We have a pair of functions that will be my probability density, which lives in minus infinity Vf interval, and the n of t, which is going to be its mean firing rate at the end of the day. But what I'm going to assume is that it's an L1 lock in time function. And the notion of weak solution is quite, well, I mean, it's just quite standard. I just integrate by parts and put everything onto the test function. But the important thing is what are the terms that appear by doing that. Take into account that the flux at the threshold was given by this minus A of n, minus n was minus A of n derivative of v with respect to v at threshold. So when you integrate by parts, this term disappears. This term appears. So that's why you have this n of t phi of the threshold voltage. This part of phi of the VR comes from the delta. The reappearance of the neurons at rest value. Okay, so probably at this point I think it's a good time to write the equations again on the blackboard somewhere. So it's dp dt plus, I hope I use the same notation, h of v n times p minus a of n, second derivative of v respect to v, equals n times the delta at the reset. And remember that n, by definition, is minus a of n. This could be just a constant partial derivative of v respect to v at the firing voltage. Oops. Okay, good. So, as I said, this term comes from the delta Dirac, this term comes from the boundary condition when you integrate by parts in the second term. When you integrate by parts here, the term disappears because of the Dirichlet condition. Remember that p has to be 0 also at the firing rate. Okay, so this I already said it before in words. In fact, the definition of n is imposed by the fact that you want an evolution of a probability density. So if you just impose to have this, you realize that exactly this is what it has to be n, it's not conserved. And now I'm going to explain you first an interesting result also it was interesting even for the computational neuroscientists, because they were doing a lot of simulation of this thing, mainly at the level using Monte Carlo, okay, with the model, just with the stochastic differential equations. And in fact, what we discovered is that there is non-existence of global in time solutions for this problem under certain conditions. So at the first sight, they were surprised, but when we explained them, they told us, yes, of course, in this situation it should be like this. But we'll explain that later, why. So the result goes in the following way. If B is positive, okay, here it's very important, B positive, then I assume that the drift is larger or equal than minus B plus Bn. In fact, I told you that the drift was exactly equal to this, to minus B plus Bn. But you don't have, for the theorem, you don't need exactly equal. It can be just larger or equal, it works the same. And I'm going to assume that the diffusion, even if it's n-dependent, is bounded below by a positive constant. So the theorem more or less goes in the following way. If the initial data is concentrated enough around the threshold value, around this threshold value in the following sense, if this interval, you can think about this interval as a particular moment, in a sense, okay? So I'm just using a multiplier. Since I'm in an interval minus infinity v, if I use e to the mu v with mu positive is perfectly nice function. So if I compute this kind of exponential moment of the initial data, and it's large enough with mu larger than that constant that depends on the data of the constants in the model, then there are no global in time solutions, weak solutions in the sense that I introduced before. Okay, how it works this? So you will see that it works more or less with the kind of ideas that you use when you want to prove non-existence of global solutions by contradiction, proving that certain thing happens that it cannot be by the constraints you have in the problem. In a sense, like when you do the Keller-Singer model or things like this, in a sense. Okay, so the idea is, let's use this as multiplier in my equation, so test function, so we use it as a test function. I just define this number because it's going to appear in the formula, and I'm going to play with it. So then you just use the notion of weak solution, use this as a test function, and I show you the proof because it's not difficult at all. Here, this larger or equal, I'm using just the fact that the h is larger or equal than minus b plus bn. If it were equal, that's an equality, and this is exactly. And I'm using also that the e of n is bounded below by a positive constant. So if the diffusion is constant, doesn't depend on n, and the h is exactly minus b plus bn, this is an equality, in fact. So just by using the weak formulation and the hypothesis, you have this bound from below. Now here what I use is simply that since I have minus b in an interval minus infinity bf, I can bound it from below by minus bf. And then I take out all of this out of this interval, which is exactly the same quantity. Okay? And here, this is what it came from the boundary value and the delta Dirac. What I keep is this minus lambda v mu times n. Of course, there I have used already that b is positive somewhere. Okay, so now let's call this function, this kind of exponential moment, let's call it m of t, m of t. Then the choice of mu makes me that this coefficient that I have in front, this guy, mu im minus bf is positive, b is positive too. So in fact, by using that, and Okay? Yeah, sorry, I go behind. You see, yeah, by just using these two things, what you get for the m, in fact, is this kind of inequality. And as I said, here is just the choice of mu and the fact that this is positive. And by choosing initially already that m mu 0 is larger or equal than 2 lambda, when it enters this assumption, enters to kill this guy with this part. Okay, you have bn times mu times this. You are going to kill it with this guy because you are assuming that initially this is already larger than whatever it has to be with respect to lambda. Okay? So in this way, if initially it's larger, that term in a small time interval, it can be done positive. And then I will have that m mu of t is increasing in time. And moreover, I have this, this differential inequality that just by Gromquist's lemma, it tells you that this quantity increases exponentially fast in time. Okay? And what is the contradiction? The contradiction is this quantity increases exponentially fast in time by this, but for a probability density function, this phi of f is, phi of v was exponential of mu v is always less or equal than this, so this is bounded. So that's the contradiction. A bounded function, in principle, that here blows up in time. Okay, so this is the first surprise with this model. If v is positive, you can always look for initial data that makes this concentrated enough around the threshold voltage, and then it will blow up in finite time. It's a contradiction argument. It doesn't tell you anything about why is the case. For which set of initial data you can do that, I mean, you have to clarify a bit that you can do that, but just by saying that you are close enough to a delta, you realize about the conditions, and then you get the result. Okay, as I said, this was first a surprise for these people, because of course they were working with this, doing numerics, and say, oh, come on, I'm doing numerics, how it can be ill-posed. But the problem is that they saw already these kind of things, because B there is positive, so this means that the network is, in average, is excitatory. So meaning for them, the conditions of that theorem are conditions that you typically don't find, hopefully, in any brain. Because you don't have, this will correspond to have some kind of epileptic attack, no? Because it will start firing in threshold as faster and faster. Okay, so they typically don't. They just told us that the conditions in which the theorem applies are not conditions in which they use these kind of models. Okay, okay. More interesting things we can do on that. Well, the next interesting question is, what about the stationary states? Stationary solutions, well, they should satisfy that equation. What I have done is formally include inside the flux the delta Dirac at the reset as the derivative of the Heaviside function. Okay, just for then just do the usual stuff with Fokker-Planck equation that you will say that the flux is going to be constant. Use the boundary conditions to say that the constant is 0. You just use the boundary conditions, Dirichlet for P, and at the end coincides with the flux, and it tells you that that constant has to be 0. And from there, at least, well, from there you can just integrate, okay? And you get this formula of P, of the stationary, possible stationary solutions. They should have that formula. In terms of n, still I haven't told you how many we have, because it's, still we have that n should be the flux at the threshold. So I have to tell you how to. Well, I have used it, but and then since you can, in fact, in order to get this formula, you have used it, and you can verify that such a function always will satisfy this flux condition. But I need something else. I was looking for a probability density. So this means that I had to impose that I have integral 1. Okay? So the integral of this whole thing in V has to be 1. Okay? So this in fact restricts for us the possible ends. So just by integrating here in V and imposing that it is 1, putting AM over N in the other side, you get that the ends corresponding to stationary solutions should satisfy that horrible integral equation. Okay? Well, it's a one-dimensional equation that you need to say how many solutions you have, but it's a horrible one. So we don't have a precise answer of how many solutions we have, because this integral formula is not that nice to work with it. Okay, so what is the theorem that we can get? In fact, by just changing variables in this formula, what you obtain for the equation satisfied by the firing rates of the stationary states is that they should be n's for which a certain function is equal to 1 over n, and that function is written over there. Okay? It's a kind of, can be written in terms of error functions and things like that. Okay? In fact, by changing variables in this double integral in UZ, very much like when you do coagulation fragmentation models and you change variables a bit and so on, integrating in a different way the set, you can rewrite all that integral in this form, which is much more manageable to do computations. So in fact, just by doing a Taylor's function of those exponential there, you see already some properties that I of n will have. So in order to answer how many cross points you have between I of n and 1 over n, what you have to study is this function as much as possible. And this you can do, and the answers are more or less here in this slide. So it's not too important, you can compute derivatives and also study a bit the derivatives. What we can show is that for V negative, I of n is always an increasing function of n, convex, and that as n goes to infinity, goes to plus infinity. So then, very good. You have 1 over n, you have an increasing convex function, perfect. Life is easy, one unique stationary point. Okay? Case B positive. Case B positive, remember, is where we had this blow-up result. So here what we can prove is more complicated because I of n is now a decreasing convex function, and we know exactly the limit as n goes to infinity of in multiplied by n, and it's given by the constants of the problem. It's the difference between the Fourier and the rest divided by b. So the thing is that now you have these your hyperbola 1 over n, and you have this function I of n, that in fact for them is not difficult also to show that at 0 is finite. So you start from a point here, and you know that at infinity is going to behave like 1 over n2, but with a different constant. So in fact, it's not that clear how many times it will cross to the other one. And that's part of the problem, because, well, you can do it numerically, and numerically it's quite clear what you have. This is from different values of b. What you have here, just look at this, okay? So from different values of b, this function that does like this is just the n times I of n. And I'm just putting for you the constant 1 to see how many crossings you expect. So as you increase the value of b, at the beginning you don't have any 1, so no stationary state. At some point you have 2, and at some point you leave off having 2 and you have 1. But I cannot, theoretically, in fact, I don't know how to estimate these values completely well. And by now the only thing that we can say is that for b small and positive, there is a unique steady state. For b a bit larger, verifying certain conditions, there is at least 1. For b a bit larger, verifying another conditions that I'm going to go into detail, I can prove that there is at least 2. And finally, under other conditions, that there are no. So if b is large enough, compared to, this means high connectivity condition. It means that the neurons feel basically everything from the neighboring ones. Okay. But still we don't know that it's exactly 1, exactly 2, and exactly no solution. That should be what you expect from the numerics. Okay? The linear case, in fact, I don't have too much time now, so I think I'm going to stop very soon. But in the linear case, I think Mar will say something too. So in the linear case, what we can show, what is linear case? Is b equals 0. For b equals 0, this problem, in fact, enters directly in the general linear entropy business, relative entropy business that Benoit introduced some years ago for many models. So you can use the same idea here. And for the linear case, you can have very nice Lyapunov functionals. For the stationary state, you have a unique stationary state, have nice Lyapunov functional, nice inequalities that tells you that you converge exponentially fast towards the equilibrium. So I will not go into detail of that, but tells you that if you are interested in, we can talk outside. The only important thing I want to remark is that the boundary condition, they enter in a relevant way. So you have a term in the entropy dissipation that comes from the boundary condition, and it has the good sign. Okay, so it's not that the boundary condition doesn't appear. It appears, but it has the good sign. Okay, and just to finish, if I have 3 minutes, I will show you some numerics to illustrate a bit what you can do. Here what we have done is simulating the PD, okay, directly. So, okay, let me see. This is a case of B positive, small, in which we have a unique stationary state. From the theory we have, first, by the way, I didn't mention that. From the theory we have no well-posedness theory. I haven't presented well-posedness theory. Okay, here. Mar will explain you how we do well-posedness theory now, that now we know, but she is exactly what she's going to do. So here, what you do is the evolution in time for B, small positive. There is one unique stationary state, and in principle, you see, for all the initial data we chose, we have a nice convergence towards a stationary state. Okay, but this we don't know how to do yet. We know how to do well-posted, but not convergence as t goes to infinity. This is the firing rate, the n, as a function of t for different cases. The first one here is when you have a unique stationary state for B positive, small. So it goes up at a certain point, goes down a little bit, and then it converges to the asymptotic value. Here is the case of a blow-up, so for B large. So basically, the blow-up appears at the boundary. So what it blows up, at least numerically, is the n of t in time. Okay, the boundary value, it seems is what is blowing up. This is a case in which you have two stationary states. So what we did here is to take as initial data something close to one stationary state and something close to the other, and plot the n of t. And what you see is that one of that seems to be stable and the other one seems to be unstable. But we don't know how to prove this. And this one is the case of B negative, in which everything also is very good and the n of t converges, and it seems monotonically as t goes to infinity to its value. And I want to show a blow up. So how typically is what we see numerically in the blow up. So for initial data which are not, in fact, not too concentrated close to the threshold. Here, by the way, I didn't explain anything, but the threshold is 2, the rest is 1. And our initial data is some kind of Gaussian over there. So after a time, what we see is that the derivative in time, so the flux, the n of t, at the threshold becomes very, very large. And then it's just the numerics, they just stop. Okay? This is as much as we can say. This is the n of t in time. And also we have done numerics for the other model I presented to you, the one in which we put together the v and the g. And that one, from the numerical point of view, is quite rich in terms of what are the kind of solutions you get. And this is the very interesting thing of that model too, that I would like to understand also theoretically, because I will just show you this picture. These are pictures of the n of t, which corresponds to the firing rate in the model, in the more complicated model with v and g, by increasing the value of what it corresponds to b in that model. So what it corresponds to the connectivity. So for a small connectivity, you have like convergence to some value. As you increase, what you have is this kind of pulsing, which looks like a periodic solution. And in fact, we computed this for a very, very, very long time, and it seems that it's a periodic solution. We don't know how to prove the system periodic solution for that model. That would be very interesting. It will interest even the computation neuroscientist. So this is as increasing the V, you have this kind of periodic solution, and after a while, when you increase the V, you have this kind of solutions, which are like these pulses, which repeat like periodically, but damped in time. Well, this is just a numerical observation by now, which coincides with the Monte Carlo simulation that some people did before, and so we think that the numerics are well done for the PD system there, but theoretically and analytically, that is completely open. So I stop here. Thanks.
Thank you for the talk. Any questions?
Your system seems to describe a big amount of neurons. Yeah?
Mm-hmm.
So how big is this number of neurons in reality?
In fact, I didn't explain. There is a scaling behind. When you do this, the diffusion approximation, you have to do a scaling between the strength and the number of neurons. So the assumption to do this diffusion approximation that they completely skip is that the number of neurons is getting to infinity, and the strength is going to 0 in such a way that n times the strength gives you a constant. So it looks like very much like this kind of Boltzmann graph limits that we are accustomed in kinetic theory. This is what the assumption is behind to do the diffusion approximation. About the number of neurons, we are talking about 10 to the 6. In a typical thing that they do in experiments, 10 to the 6. In the brain, there are much more, but I mean, in the small piece that they are studying, yeah, 10 to the 6.
Any other questions or comments? Okay, we will have some time to discuss. Let's make a short break. Let's say we start at 3:10. And thank you again.